Explain the difference between an amorphous and a crystalline solid at the microscopic level. Describe the structure of a network solid. What holds it together? How is it different from other types of solids? And what physical properties of the solid are affected by this structure? So the main difference between amorphous solids and crystalline solids simply has to do with how the particles are arranged at the molecular level. Amorphous means without shape. The particles in an amorphous solid are very disordered. They have high entropy. They are randomly arranged. They're kind of messy. Whereas in a crystalline solid, you have these highly ordered molecules in a repeating pattern that are highly organized, have very low entropy. This arrangement of particles leads to a couple of interesting differences in the properties of amorphous versus crystalline solids. First has to do with their melting point. Amorphous solids don't tend to have a very sharp melting point. They don't get to a certain temperature and begin to liquefy. Instead, they have a tendency to kind of soften over a range of temperatures. And this just has to do with the fact that their arrangement is random. And so they don't have a specific type of force, or the forces vary that hold them together. Whereas in a crystalline solid, there is a very sharp specific temperature at which it melts. Ice, for example, is a crystalline solid that melts at exactly 0 degrees Celsius. Another difference between the two types of solids is this property of anisotropy. Now, this is kind of an obscure vocab word, but what it means is that the substance will have different properties in different directions. Now, this is kind of a weird concept, but an example that you can use is if you think of a piece of wood, like a log. If you are splitting wood, it splits very easily in one direction, but if you turn it on its side, it's very difficult to split. This is an example of anisotropy. In a chemical compound, for example, a crystal, you may have a crystal that scratches very easily in one direction, but is very hard in a different direction. Or maybe it splits very easily in one direction, but it doesn't split in another direction. So amorphous solids are what's called isotropic. They do not have anisotropy. So they are the same in all directions, whereas crystalline solids will sometimes have properties that vary in direction. Some common examples of amorphous solids that are often used on the AP exam are glass, which is silicon dioxide, rubber or latex. Most plastics, such as polystyrene, are amorphous. I want to just for a second mention here that there is another form of SiO2 called quartz, which is not an amorphous solid. We'll talk about that in a little while. Crystalline solids can really be broken up into two types. You have ionic substances, such as table salt, and then you have molecular solids like ice, where you have molecules that are simply arranged in a regular repeating pattern. Metals as well also form crystal structures that are highly organized. So most metals, when they are in their solid form, are crystalline solids. This diagram shows rubber in two different forms. It shows it in its normal form on the left here, which is highly disorganized. It has these long chain molecules that kind of wrap around each other. But when you pull it, those long chain molecules kind of elongate and hold each other together. And this is why rubber is allowed to stretch and then recompress when you let it go. Here we see a diagram of NaCl at the molecular level, and you see that the sodium ions and the chloride ions repeat themselves in a very regular pattern. And you can tell that this cubic structure that we have on the microscopic level repeats itself so many times that we see that same cubic structure. We see these 90-degree angles in the macro scale. When you look at salt crystals under a microscope, they have perfect 90-degree angles. They're very, very cubic in nature. The idea here is that the microscopic arrangement of particles often shows itself on the large scale. Ionic compounds also have a unique feature where they tend to cleave or break along very straight lines. Now, the reason that this happens is because when there is stress put on the crystal realigns itself so that the positive charges and the negative charges end up next to each other. And when that happens, you get this line where there are repulsive forces that push the ions apart. And this happens, like I said, in a very straight line. So you get these nice flat planes where the crystal breaks apart. This diagram shows water molecules that are locked in place when the kinetic energy gets slow enough that the hydrogen bonds that are holding the molecules together really cause the molecules to orient themselves in a very specific pattern. And you get this nice repeating pattern of water molecules that is in a hexagonal structure. And again, you can see that the hexagons that form on the molecular level are responsible for the fact that ice crystals form in hexagonal shapes, as you can see in this microscopic picture of a snowflake. Another interesting thing about ice, water ice, is that there are these gaps in the middle of the hexagons that are empty space. Now, when the water is in liquid form, you don't have these gaps. This only happens when the water freezes. And so when water freezes, these gaps form, and you actually get expansion, which is why when water freezes, it expands, it gets larger. It's also why solid water is less dense than liquid water, which is actually a pretty rare property for most substances. Most substances, the solid form is actually more dense than the liquid form, but that is not the case for water because of its unique crystal structure. Part B says to describe the structure of a network solid. What holds it together? How is it different from other types of solids? And what physical properties of the solid are affected by this structure? So a network solid is a very unique type of solid where you have a 3D web or a lattice where every single atom that's in the lattice is covalently bonded to all of its neighbors. This essentially creates one giant macromolecule. There are no individual molecules in a network solid because everything is connected. So a molecular solid has individual molecules that are held in place by intermolecular forces. So, for example, water ice that we just talked about is held together by hydrogen bonds, or if you have something weaker, like if you have hydrogenated vegetable oil, that type of solid can be held together purely by London dispersion forces. So the forces that are holding together molecular solids, intermolecular forces, are much, much weaker than covalent bonds. And because of that, they are generally softer and have much lower melting points than network solids. Ionic solids are held together by electrostatic attraction, by Coulombic attraction between the positive and negative ions. They are generally very hard, however, they can break easily, and that again has to do with the fact that the positive and negative ions will repel each other if the crystal lattice shifts even a little bit. Network solids, however, have continuous covalent bonds, and so they also have very, very high melting points, in general, even higher than ionic compounds, but they can be much, much harder and tougher than ionic compounds. So as I mentioned before, network solids in general have very, very high melting and high boiling points. For example, a diamond has a melting point of over 3,550 degrees Celsius. They are very hard and very strong. Diamond is one of the hardest known natural substances. An interesting thing is that network solids will have variable conductivity. So, for example, diamonds do not conduct electricity, and diamonds are a form of carbon. However, graphite, which is also a form of carbon, is highly conductive to electricity because it has these delocalized electrons. Here are some of the most common examples of network solids that you are going to see on the AP exam. Diamond is carbon where every carbon is bonded to another carbon in a three-dimensional structure, so this goes in all different directions. Each carbon here is tetrahedral in shape. When you have graphite, graphite is a different form of carbon where instead of having a three-dimensional structure, you have more of a two-dimensional structure. So carbon bonds in these hexagons where each one is trigonal planar rather than tetrahedral, and you get these large sheets of carbon that kind of sit on top of one another. And there are delocalized electrons above and below each sheet, and that allows graphite to conduct electricity because those delocalized electrons can move around very easily. Another thing it does is it allows these sheets of carbon to slide past one another very easily because this sheet of carbon has a negative cloud below it. This sheet of carbon has a negative cloud above it. And so they repel one another and they actually slide off of one another almost like sheets of paper. And because of this, this is how pencil lead, which is actually graphite, is able to write so easily. When you slide the tip of your pencil across the paper, what's actually happening is that these huge sheets of carbon are sliding off one another and onto your sheet of paper. Another form of carbon that you will see sometimes, which is actually very rare, is what's called a fullerene or a Buckminster fullerene, if you know the full name of it. It's a ball of carbon. It's like a soccer ball where you have alternating pentagons of carbon and hexagons of carbon. Often if you split one of these in half and then you create a long tube with half of a fullerene on either end, they call that a carbon nanotube. I mentioned before that silicon dioxide, which is what glass is made of, can also form another network solid. This is called quartz. It's the same chemical composition. However, here you have a very regular pattern of silicon and oxygen, where each silicon is bonded to 4 other oxygens, and each oxygen is bonded to 2 silicons, and you have a network of covalent bonds. The last one is silicon carbide, which is a mixture of silicon and carbon. Silicon and carbon are directly on top of one another. They're in the same group in the periodic table, so they have very similar chemical properties. They bond in very similar ways, and so they are able to form a network solid that's very similar to diamond, but is much easier to create and has a lot of industrial uses. And the last thing I wanted to show you is just the difference between glass and quartz on a molecular level. Both are made of silicon and oxygen in the same ratio. However, glass normally forms this amorphous structure where everything is a little bit messy. And this generally happens when things cool very quickly. When things cool quickly, the molecules don't have enough time to form an orderly structure. Whereas if you cool them very slowly, you get something like this on the right. This is quartz, where you have a very, very rigid network solid of silicon and oxygen.